All right, so let's start a new part. I think in the last couple lectures, we have kind of finished the part of regression. So in the next part, we're going to focus on classification. So what is the classification? Is the key is my target Y is actually like discrete class labels. It's not like some continuous target. I mean, if it is continuous target, then this can be done using regressions. If it is discrete, like we want to distinguish cats and dogs, this is a typical classification problems. And basically, and we want to create a model and build a like discriminative classification models. So this P, Y given X and theta. Okay, so this X right here is some fixed dimension. Input vectors. So this X is actually in, say, in R small d. And Y, as I said, they are in discrete class labels. And also, I mean, this theta right here is some parameters. So you can build your models based on how you and how you model this and the probability distributions. If C is equal to 2, I mean, this is called binary, like, and logistic regressions. So in these cases, we will use Y is equal to, in general, we will use Y equal to 0 and 1s. If C is bigger than 2, that means, for example, we are trying to classify the MNIST data set. This becomes multinomial in the logistic regression and the logistic regressions. Sorry, I want to emphasize the first model for the classification in this courses is the logistic regressions. Although this is called an logistic regressions, it is actually a classification problems. We're trying to make like classification models directly. So that's why I'm saying when C equal to 2, then this will becomes binary logistic regressions. When C is bigger than 2, this becomes multinomial and the logistic regressions. Or, I mean, there's no way called like multi-class and the logistic regressions. Okay, so these are, I mean, just a different names for that. So, and for this And for this lecture, we will just focus on the binary part. In the later of the lecture, we will talk about and the multi-class. So for the binary, you can actually think about an examples as being so my input is the image, like pixels of image. And my output is, and whether it's a cat or dog. Right. So I mean, so we need to build a model for this probability right here, right? So we need to and build this like discriminative classification models for the given features X and then the output of Y. So here is the model. Here is the model for binary logistic regression. So again, we have a feature X is basically X1, X2 to X of D, which is in RD. And we're going to adding a bias here. So we're going to rewrite this. This is, I'm going to adding 1. D plus 1. So this add bias. Like what we did in the like regressions. Then we have a weight. It's very similar to regressions. W1, W2, and the first one W0 to WD. So I'm going to call this column here. Of course, this is also D plus 1 and dimension. So I'm going to define, again, it's very, very similar to and the linear regressions. So I'm going to define the pre-activation value. So I'm going to call the pre-activation. Z is in the product between X and W. So we know this is the row, this is column. So this is a row that means 1 by D plus 1. This is D plus 1 by 1. So this is a scalar R. So then with that, I'm going to make a prediction of the linear classifier. Say phi that my phi z is equal to 1 if z is bigger than 0, is 0 if z is less equal than 0. So this is called Perceptron. So this whole model is called Perceptron. Okay, and later you will see these things again. So basically, this perceptron has 2 steps. One is linear model, which is X inner product of W. W is my parameters. plus some binary step functions, which is phi right here. So basically, this is compositions of both of that. So I mean, my y is actually just my phi of w dot inner product of x. So this is a linear model. This is binary step function. So this phi has another name, as I said, and here we call it pre-activations. So the reason we call it pre-activation is because this phi is also called activation functions. And of course, there are multiple other activation functions. This binary step function is the first one that we have encountered. The parameter that we're interested in is the W. It's just my W right here, which is in D+1. That to be learned. So and hypothetically, if we can find as optimal W right here, then we have input my X, which is my feature. Then we apply this binary step functions. It will automatically give me Y and zeros. And I hope for all the training data that we have, we can so we can as much as we could to separate those data sets. All right, so and you see, I mean, everything is like linear separate, right? So you can think about I'm actually using a linear model to make the classification. So in geometry, so what does that actually mean is the following. So we have, say this in 2D data, that we have some circles right here and a cross right here. We have some circles right here. So what does the perceptron is doing is we're trying to learn a straight line, and this, I mean, straight line is basically y equal to xw right here. Xw right here. Yes, some value here. If everything above this line, I will be classify everything into +1. Everything below this line, this will become 0. So this is the geometric pictures of and the perceptron. So and the whole idea is we actually want to learn this like linear separator to separate these two datas with a different and with a different labels, and a 0 and a 1s, using in a straight line. In this cases, if we are working in high dimension, this will be just a hyperplane. Okay. And of course, the key is we want to find out this hyperplane that can hopefully perfectly separate these two data sets and the 0 and the 1s. All right, so you can view everything in terms of the following and a graph. And you will see this and something later when we start to talk about neural network. So this is, we have 1, which is just some bias. We have x1 to x of d. Okay, so I'm going to assign into different weight, which is w0, W1 to W D right here. So these are actually the weight. Then I'm going to, and what they do is multiply them together. So these actually are my features, feature input. All right. Then this is some constant here. So you are going to multiply them together. So x1 times w1 and so on. Then you sum them together. So this is a big summation here. It's like weighted sum. Then apply the step functions. This is step function. So everything beyond 0, it's 1. Everything below 0, it's a 0. This is step function. And this will be output. It's either 0 or 1. Okay, so this is and it's just a simple two-class classification problems. It's just you can think about it, we are using a single neurons that used for this and two-class classification problems. And this is the foundation actually to a neural network. And later on, and we can build a layer and the layers and make things more complicated. But everything just built on this and the little part right here. So now the question is how to find W and how to train W. Right. So so I want to remind you. So we need to give and we need to find the loss. So basically we're given the training data set D. Yi I from 1 to D. And so this is, my training data set. So I'm going to write so loss function. So my loss function is basically and you can think about a mean square error. So what I'm going to do is I'm going to take this summation from I1 to the n of yi minus phi. So this is my model phi, x of I, w, these are all vectors, square, and divided by n. So this is my loss functions. So the key is we're trying to find out the optimal w, actually minimize that. So that will be argue mean of my w right here. And of course, this is also, you can think about the residue sum of square ISS, which is the same. So, and you can see, this is actually my loss function right here. I'm going to call this big L of W. But if we look this closely, so this can be in general written as 1 over n summation I from 1 to the n of big L of I of W. So this is the loss function for each component and each data entries of the training data. So this is square. So this is basically if we only get I data entries for xi and yi, then we calculate the and the square errors between the predictions, and the ground truth. But I want to emphasize there's something here. So we only work with the 0 and the 1s, right? So the output of this is 0 or 1s. This is also 0 or 1s. So that means this error, it's either 0 or 1. I mean, if it's 0, that means the prediction is actually accurate. If it is 1, that means the prediction is actually wrong. So, I mean, there's no other middle values. I mean, it's either, correct or wrong. Right, so this is something that is quite clear. It's more like accuracies. Okay, but the issue is this gradient. I mean, of course, we can take the gradient of this is equal to 1 over n gradient of this. But biggest issue is this is not differentiable. Why? Is because this step function right here, this phi here is not differentiable. So there's no way that you can do gradient descent. And just because this phi is discontinuous, and the gradient is actually 0 almost everywhere. So basically, this is a big issue here. Phi is really bad functions. I mean, the point of this phi is just either 0 or 1. So there's no gradient informations. If something has no gradient, something has no gradient information, it will be very difficult to learn. But in any cases, we could actually mathematically write it out. If we actually write it out, this is being phi of x of I, w, y of I, and the phi prime of x of I, then dot x of I transpose. So the problem is coming from this one. This part is not differentiable. So, as I said, this thing is 0 when z is not equal to 0, is undefined. It's not defined. When z is 0. So how can we do that? In practice, in machine learning, or in applied math, or even like computer science, if we see something that is really hard and we don't know that, we just get rid of this. And hopefully, this could give you a good approximation to it. So this is not accurate, but hopefully this is good enough. So this is basically says we still need some gradient information. But I'm going to say, I know this part is not differentiable, but I just don't look at that. That's how the mentality it is. So I'm going to just using the first part and the second part, and the first part and the third part, and completely get rid of the second part. Okay, so this is your fake gradient. So, and we call it fake gradient. But this actually can give you a good, and we can write down the gradient descent. So the gradient descent is basically says this w t plus 1 is WT subtract eta of summation of I from 1 to the n of this fake gradient part. This is y. Okay. So this is your gradient descent scheme. But although we're using the fake gradient, it somehow makes sense, right? Because if these things is equal to y of I, so because my input is always so my output is always 0 and 1. If they are equal, then no change is needed, right? Because this component just becomes 0. So if this whole thing subtraction is I'm equal to +1 or -1, so I'm going to move the weight in the direction so that it make correct answers more likely. So I'm going to move the weight in the direction to make correct predictions. So this is the point. So this is actually the directions, and which is along, the directions of the x of I. One of the issue here, this is my gradient descent scheme. One of the issue in like machine learning is we usually have the problem is n is very large. If n is very large, to calculate the gradient, that would take really long time. Right? That's really, really expensive to sum all of the component together just to move one step of my W here. And this won't be efficient in high dimension anyway. So that's why this this gradient descent will not be efficient. So so how can we make things more efficient here? Is I want to update it quickly, and rather than I have to calculate the gradient for the whole data batch. So that's something can be done called stochastic gradient descent. So this whole idea is very and very clear. So I'm going to actually demonstrate that and with programming. So basically, so like initialize your W0, which is your an initial vector of the parameter, and your learning rate eta t. So what you do is you repeat until converge. As until the minimum is reached. So what you do is, the first thing is you randomly shuffle the samples. In the training set. And update eta t. So basically you need to shuffle the data so randomly. Then you do it in the order for I 1, 2 to the n. So this is called one epoch. And with that, the eta t is a constant. And within one epoch, and eta t, which is my learning rate, is a constant. So my W is being updated as eta t of phi x of I, W subtract y of I of x of I transpose. So this is basically being updated constantly for W's. In fact, there are two things I want to emphasize. You basically, this is your data right here. Your data with x1 to x of n. So then you reshuffle the data. So say this becomes x of 10. The last one becomes x of 53, and so on. So then you feed your data one by one. If you feed m data one by one from the first one to the last one, that will consider to be one epoch. And during this epoch, for the updating of my W, my learning rate remain this constant. So basically it will be the same in these cases. So this is something called stochastic gradient descent. So in theory, this convergence of stochastic gradient descent is also called SGD. Is slower than batch gradient descent. But in practice, stochastic gradient descent is often faster because each step, the time needed is much, much smaller because we only need to calculate one data gradient, then we can make a move. Such that this gradient and stochastic gradient descent can make faster progresses than with the full batch gradient descent. So right here, we are using full batch gradient descent. So here we actually need to find out the gradient for all n of that, such that we can make a movement. In this cases, we only need to calculate one data gradient. Then we can update our W's. So that's why everything will be much, much faster. So in terms of in terms of that. This is particularly helpful in the beginning of the training because in the beginning of training, those parameters are not well estimated. It's not worthwhile to carefully evaluate the gradient at all. It just gives you some idea which direction it should be going. We should go this way. That would be, sufficient. It doesn't necessarily, it's not necessary to use the full batch to carefully calculate gradient to know exactly which direction we should go. This is not necessary if this is part of the early trainings. In order to this SGD to converge, there are, a condition need to be satisfied. So, so this is something called like Robin-Monroe condition. So this is Robbins-Monroe condition. So this condition says my learning rate eta t has to go to 0 as t goes to infinity. And actually, there is some like additional condition that need to be satisfied, that t from 1 to infinity, the eta t squared divided by sum of t from 1 to infinity of eta t. This also goes to 0. So that means summation of eta t squared should goes to 0 faster than summation of n of the eta t. So there are a couple very useful choices of the learning rate. For example, piecewise constant. So that means I have maybe at like first 10 epoch, that would be this, and the rate, then we drop, then we drop, then we drop, and then we drop, then something like this. So this is maybe 10, this is maybe 20, and so on. So this is called piecewise constant. So this is my eta of t, and the versus t is the, and right here is the number of epochs. Another one is exponential decay. So this is basic, say I have eta of t and I have t right here. I'm going to decay like this. So this is exponential, so eta 0 of exponential minus lambda t. Another one is polynomial decay, which is commonly used right here. So this is your eta t. This is your t. Polynomial decays slower than so exponential. So this is could be something like eta of t 0 of beta t plus 1 minus alpha. So this is some like polynomial decays. All right, so let's see. Okay. But there's also another one that is like in practice we just use, but it's not really good. But we use anyway. Turns out sometimes it can work very well. That we just assume eta t is just a constant. Small, but small. Okay, so that's okay. But sometimes it just and work nicely. So So let me show you some plot here. So this is, I mean, if you're trying to like find the local minimum of this function with the corresponding contour, if you're using gradient descent, this will just go smoothly and hit this rest dot. If we're using stochastic gradient descent, it turns out it will like zigzag and wandering around. The loss functions is not necessarily monotonically decreasing, as you can see it might increase, but eventually it will start to decrease, and it will decrease slightly slower than the gradient descent, but eventually it will and it decrease to our desired end result. But you can see, and right here it will do zigzag, and it's not necessarily and monotonically decreasing as what we had for the gradient descent. So this is a fundamental difference between gradient descent and the stochastic gradient descent. And we're going to talk about a little bit theory in the next lectures. I mean, this is just give you some heads up and what kind of problem that we're handling right here. Right. So all right. So this is good. And then let me just try some very simple programming right here. In practice, and you can just try some constant learning rate first, then tune this learning rate gradually later if you need it. Okay, so this is a very simple one. So we write this perceptron and this activation functions very quickly. So we have this pre-activation value is just x dot w. And we know output will be 1 if activation is bigger than 0, if it is 0 otherwise. So this is nothing but we just copy paste what we already have. The second thing is we're going to train this weight, right? So I mean, this is my training function, and obviously it's very important. So we have this x has the shape of n by m. And what we do is we are going to run this number of epochs that we have. We initialize the error. So shouldn't have this part. Then what we are going to do is we're going to reshuffle this index. I mean, instead of we should and shuffle the x, we can also just reshuffle the index. That's perfectly fine. So then what I'm going to do is I'm going to call this for I in the ARR. ARR is already being shuffled randomly. I'm going to make the predictions for ith index versus the weight. So that means I'm going to, and this is a single vector. This is a single vector. I'm going to make prediction based on prediction function that we had. So this will be my prediction. So either 0 or 1. Then I'm going to calculate the error. And I'm going to square the error and sum them together. Then I'm going to update if the error is not equal to 0, because if error is 0, there's no update. So there's no need to update. So this will be learning rate times error times x of I. So as suggested right here for this and the stochastic gradient and the descent methods right here is being done. So this is the error. This is your xi directions. Okay, so this will be, and you do this for a number of epochs weight. If the sum of error is equal to 0, then it will stop, right? So because that means we already reached the 0. We don't, need to and further training, because the 0 is the minimum of the error that we can get. So if we hit the error to 0, that just indicate all the data are perfectly separated. All right, so this is simple data that we have. I mean, this is very simple data. We have 2D and 2D data here. The first thing that we need to do is we are going to stack column ones in the first. Because we have mentioned it right here, we need to include this bias terms right here, right? So this is very similar to the, linear regression. So if you want to, introduce the bias, you have to stack ones in front. So with that, and that becomes so we create a new data matrix of X, which is has 3 columns. So this will be, I believe it's the rows is 10. So we have a 10 data in 3 columns. So you can see this 5 point is and a bunch of and corresponding to the class of 0. This portion and corresponding to the class of 1. So 0 and versus 1 in 2D planes. So there's a possibility we can draw a line right here, right, to perfectly separate the orange dot and the blue dot. So what we're going to do is we're going to run this for 5 epoch with a learning rate of 0.1. So this is a constant learning rate. So we always start with a constant learning rate, and gradually, if we need it, we can just make things and this learning rate to be smaller and smaller. So we train our weight. And you can see right here, after 3 epochs, the sum of error just give you 0. And we print out the weight, so this will be your weight. What does that mean? So that indicates we find a line actually can perfectly separate blue point and orange point. We can actually plot this out. So this is the line actually we're getting right here. So we can see, if we draw, the line like that, these are my blue points, these one, and my orange point, it can perfectly separate these 2 data sets and without any problems. But the issue is, okay, so here is some and heads up. Unlike the gradient descent, this perceptron algorithm doesn't always converge because we use the fake gradient. That's not the real gradient. We just see this 5 prime is we don't know how to handle that. We just completely get rid of this. For this specific examples, it converges to the global minimum, which is perfect classifications. So that means the training set is completely linearly separable. And also this optimal W star can define a hyperplane. So under this hyperplane in the classification setting is called decision boundaries, right? And everything above this line that will be classified as blue, and everything and below this line, this will be classified as an orange. So that means we actually define the hyperplane or decision boundaries to separate these 2 classes perfectly. But that's not always true. In general, in the homework, you will have some data set that it's not possible to separate linearly. Okay, so it's in some senses this error cannot actually goes to 0. So in more general and a multi-layer, and you can stack them together, you can compose it like several linear and nonlinear functions. This is prototype of the modern deep neural network. To the end of the semester, we're going to talk about many new new materials and new stuff on a deep neural network, and we will review this part and later on. Okay, so that's all for this part for now.